Tonight, drift back 66 million years to the last day of the dinosaurs and to the world that grew from the wreckage of the day after. A rock 12 kilometers wide ended 180 million years of biological dominance in a matter of weeks. What survived, how it survived, and what it eventually became is a story that runs directly into the present, because the world it built is the one that exists now. 66 million years ago, Earth was running at a scale that is difficult to hold in mind. The planet was several degrees warmer than it is now, with no ice at either pole and dense forest covering land masses that have since been reshaped by continental drift. The oceans were shallow and warm across their margins, teeming with life that had no modern equivalent. On land, animals that would dwarf anything alive today moved through landscapes that stretched unbroken for thousands of kilometers. The dinosaurs had not arrived at this point quickly. They had been building toward it for nearly 180 million years, through multiple earlier extinction events, through shifts in climate, through the slow drift of the continents beneath their feet. Each pressure had pruned some lineages and opened space for others, and the result, by the late Cretaceous, was an ecosystem of extraordinary depth and variety. Hadrosaurs, the duck-billed dinosaurs, moved in herds across floodplains, processing vegetation with specialized teeth that no other animal has evolved before or since. Triceratops traveled in groups, their frill and horns shaped by millions of years of interaction with the predators that hunted them. Above the forests, pterosaurs with wingspans wider than a car is long rode thermal currents between the coasts. At the top of this system stood T-Rex, not as an isolated predator, but as the endpoint of a food web that had been building in complexity for longer than most extinction events last. What that depth of complexity meant for what was about to happen is something the fossil record has spent decades making clear. But the very thing that made the Cretaceous world so extraordinary was also what made it so completely vulnerable. A system built across 180 million years of co-evolution is not adaptable on short timescales. Every species in it had been shaped by conditions that had remained broadly stable for geological ages, stable enough that the kinds of rapid, catastrophic disruption that would require a different set of capabilities had simply never arrived. The dinosaurs had survived earlier extinction events, but those events had been slower, more regional, more survivable by organisms that could adjust over generations. What was coming was none of those things. But there was no signal. The Cretaceous had no warning system for what was approaching. The asteroid crossed the orbit of the Moon in roughly 30 seconds. It entered the atmosphere so fast that the air in front of it had no time to move. It compressed and superheated ahead of the rock like a wall, but the rock did not slow. An event traveling at 20 kilometers per second does not announce itself. The last day of the Cretaceous looked, from the ground, exactly like every other day that had come before it. But the ecosystem that looked so permanent was about to encounter a disruption unlike anything in 180 million years, one that operated simultaneously across every environment on the planet, on land and in the water and in the air, without leaving any part of the world outside its reach. The Cretaceous was not a world in decline. That is the first thing to understand. For decades, scientists debated whether dinosaurs had already been weakening, whether the asteroid simply finished off something that was already failing. The fossil record closes that argument. Right up to the final geological moment before the impact, large herbivores were grazing across North America, Asia, and South America in numbers comparable to the great herds of the African savanna today. T-Rex was at the top of a food chain that had been functioning without interruption for tens of millions of years. The ecosystems were not fragile. They were mature, interlocked, and operating at full capacity. When the asteroid arrived, it did not hit a weakened world. It hit the strongest version of the Mesozoic world that had ever existed. 180 million years of biological refinement compressed into a single moment of total erasure. The scale of what was lost only becomes real when you hold that fact clearly. The planet's most complex land-based ecosystems were dismantled not over centuries, but over weeks. The dinosaurs were the visible layer of a system that ran far deeper. Beneath them were the plants, the insects, the fungi, the soil bacteria, all of it co-evolved, all of it dependent on the stability that the Cretaceous climate had maintained for millions of years. The asteroid did not just kill the large animals at the top, it broke the architecture underneath them. That is why the extinction was so total, and why recovery took not years or centuries, but millions of years to produce anything resembling what came before. If you're finding this interesting, a like helps more people find their way to this kind of content while they sleep. The Cretaceous was a world at full capacity, 180 million years of biological complexity, running without interruption, right up to the moment it ended. But what that ending actually looked like in the hours it unfolded is something most accounts pass over quickly. A 12-kilometer rock hit a shallow shelf of sulfur-laden seafloor at 20 kilometers per second. And the specific geology of that location determined not just the scale of the immediate destruction, but the mechanism that would kill animals on every continent for years afterward. The asteroid that ended the Cretaceous had been traveling through the solar system for millions of years before it reached Earth. It was approximately 12 kilometers wide, roughly the distance across a mid-sized city, and it entered the atmosphere at a speed of around 20 kilometers per second. At that velocity, the atmosphere itself offered almost no resistance. The rock did not slow meaningfully before it made contact with the seafloor of what is now the Yucatan Peninsula. The geography of the impact mattered enormously. A different location, deep ocean, granite bedrock, would have produced a catastrophic but more contained event. The Yucatan Shelf was shallow, and the specific geology beneath it would determine what went into the atmosphere in the seconds after contact. What went into the atmosphere, in turn, would determine the fate of nearly every species on the planet. The Chicxulub crater that formed was approximately 180 kilometers across and 20 kilometers deep. The energy released in the first seconds exceeded the combined output of every nuclear weapon ever built by a factor of billions. A column of vaporized rock and superheated gas rose through the atmosphere and beyond it, ejecting material into low Earth orbit, some of which would return within hours as a rain of superheated debris falling across the entire planet. Not just the region of impact, but every continent, every ocean, every forest that had been growing undisturbed since before the first dinosaur ever existed. But the scale of energy released in the first seconds did something that no earthquake or volcanic eruption had ever done in Earth's history. It fractured the seafloor across a zone wide enough to swallow a small country, drove a pressure wave through the ocean that moved faster than sound, and sent a column of material upward that punched through the entire depth of the atmosphere before gravity began pulling it back. The Gulf of Mexico, in the first hours, was effectively emptied along its margins and refilled multiple times as the displaced water oscillated in waves hundreds of meters high. But what was happening underground in the first moments was, in geological terms, as significant as what was happening above it. The pressure wave that moved through the Yucatan bedrock after impact traveled outward at velocities that liquefied rock across a zone stretching far beyond the crater itself, and the rebound of that pressure, the bounce of compressed rock releasing, sent a second wave of energy upward through material that had already been structurally shattered. But none of that immediate violence was the event that would determine survival over the following years. The shock wave would pass, the fire would burn through available fuel and stop. The tsunamis would recede. What would not recede was the material that had reached the stratosphere in the first minutes, because it had entered an environment where the conditions that normally clear contaminants simply do not operate, and what entered that environment would remain there for a duration the surface world would have no choice but to survive through. The first hours of the impact were not survivable for most life within thousands of kilometers of the Yucatan Peninsula. The fireball that expanded outward from the Chicxulub crater reached temperatures hot enough to ignite forests across the continent without fire ever touching the ground. Radiant heat alone set North America burning within minutes. The shockwave that followed flattened everything the heat had not already destroyed. Animals that survived both faced a third phase, the return of superheated ejecta falling back through the atmosphere globally, turning the sky briefly into an oven across much of the planet. But the impact's most consequential damage was not the fire or the shockwave. It was what the asteroid vaporized on its way through the seafloor of the Yucatan. That region was loaded with sulfur-rich rock, anhydrite, and gypsum, and the collision converted hundreds of billions of tons of it into sulfur dioxide in seconds. That sulfur went directly into the stratosphere, and once there, it stayed. It would become the driver of a slower, colder, and ultimately far more lethal phase of the catastrophe than anything the first day produced. The first hours killed through force and heat. The years that followed killed through darkness and cold. The asteroid itself was only the beginning of the sequence. The real extinction engine was already in the atmosphere before the fires had stopped burning. The fires, the shockwave, the tsunamis, those were the first hours. But the animals that survived all of that still faced something the immediate violence could not prepare them for. The material the impact sent into the stratosphere was not going to come back down. It was going to stay, spreading pole to pole within weeks, blocking the sunlight that every living thing on the surface depended on, and setting in motion a period of darkness and cold that would last long enough to collapse the base of every food chain on Earth. In the hours after the impact, the sky above much of the planet was on fire. The ejecta falling back through the atmosphere generated enough heat to ignite surface vegetation across wide areas without any flame making ground contact. Forests that had never experienced fire burned simultaneously across multiple continents. The smoke from those fires rose into the upper atmosphere, where it joined the sulfur dioxide already being carried upward from the Yucatan strike site. Sulfur dioxide, in sufficient quantities, does something specific and devastating in the stratosphere. It reacts with water vapor to form sulfuric acid aerosols, tiny droplets suspended high above the weather systems that would normally wash contaminants out of the air. Unlike soot, which can eventually be rained out, stratospheric sulfate aerosols are extremely stable. They spread laterally across the globe within weeks and remain suspended for years, forming a layer that reflects incoming solar radiation back into space before it can reach the surface. The planet, that had been 4 to 10 degrees warmer than today, with no polar ice and vast equatorial forests, was now sealed beneath a layer of particulate matter and sulfate aerosols that blocked a significant portion of the sunlight that every living thing on its surface depended on. The fires had not yet finished burning when the conditions that would define the next 2 years and determine which species would still exist at the end of them were already locked in place above the clouds. But the aerosol layer was not uniform, and its effects were not immediate everywhere at the same rate, which meant that some regions experienced the onset of darkness and cold faster than others, while organisms that might otherwise have moved toward warmer or lighter zones found those zones contracting around them faster than any migration could accommodate. There was nowhere to go. The layer was global. It spread from pole to pole within weeks, carried by stratospheric winds that circle the planet continuously, far above the weather systems that might otherwise have disrupted it. But every land surface on the planet received the acid precipitation that followed, and it fell on ground that was already dying for lack of light, altering the soil beneath plants that had no light to grow by and no chemical stability left in the ground to grow from. The two processes did not arrive separately. They compounded each other, and the combination made any prospect of near-term recovery on the land surface significantly harder than either disruption would have been alone. But the timeline that makes this period so lethal is the one most difficult to hold clearly. 2 years of darkness does not sound long against a geological backdrop. Against a biological one, it is a span during which an entire generation of large animals could live and die without ever seeing conditions return to anything that could support them. Long enough for food chains to collapse completely at their base. Long enough for animals that could not store or find adequate calories to exhaust every available option. Long enough for a warm world to become something that the organisms built for warmth had no path through. The darkness came fast. Within weeks of the impact, enough soot and sulfur aerosols had spread through the stratosphere to block a significant fraction of incoming sunlight across the entire planet. Photosynthesis did not slow down, it collapsed. Plants that had been growing in warm, stable conditions for millions of years had no mechanism to survive sustained darkness. They died where they stood, across every biome on Earth, from the equatorial forests to the higher latitude woodlands. The temperature drop followed. Global average temperatures fell by somewhere between 15 and 26 degrees Celsius over the course of months, and they stayed there. The planet did not simply get cold. It got cold while simultaneously being drenched in acid rain as sulfur dioxide mixed with atmospheric moisture and fell back to Earth. Soil chemistry changed. Water chemistry changed. The conditions that had supported plant life for hundreds of millions of years were gone, simultaneously everywhere. The nuclear winter was not a dramatic backdrop to an otherwise manageable catastrophe. It was the mechanism by which a local impact became a global extinction. An animal that survived the fireball in Asia, or the tsunamis in the Pacific, or the shockwave in Europe still faced 2 years of darkness, plummeting temperatures, acid rain, and a food chain that had ceased to function at its base. Survival was not about being far enough from the impact. It was about being a type of animal that could keep living when almost nothing was growing anywhere on Earth. The nuclear winter did not kill randomly. What determined survival had nothing to do with the traits that had defined success in the Cretaceous. Not speed, not size, not predatory capability, not any of the adaptations that had been refined across millions of years of competition. The rules that governed who lived through the next 2 years were entirely different from the rules that had governed the world before the impact, and most living things had no idea they were playing by the wrong ones. When the impact winter settled over the planet, the immediate question was not which animals were strong enough to endure it. Strength had nothing to do with what was coming. The question was which animals' daily requirements for food, for shelter, for warmth happened to be compatible with a world in which surface temperatures had plummeted. Plant life had largely ceased to function, and the food chains that had fed the largest animals on Earth for millions of years had collapsed at their base. The large animals of the Cretaceous had evolved in conditions of abundance. A T-Rex required enormous caloric input to maintain its body mass. Estimates suggest several large prey animals per week at minimum. Sauropods, the long-necked giants that had dominated earlier periods, needed hundreds of kilograms of vegetation daily just to sustain basic metabolic function. Even mid-sized predators like the dromaeosaurs depended on prey populations that were themselves dependent on a functioning plant base. When photosynthesis collapsed and plant life began dying globally, the animals at the top of these food chains were not insulated from that collapse. They were the most exposed to it because they were the furthest from the base and the most calorie-dependent at every link in the chain. Meanwhile, in burrows beneath the frozen ground and in the mud of river margins, other animals were still there, waiting out a set of conditions they had not chosen and could not have anticipated, in the dark, with no indication that the world above them would ever look the same again. But survival in the first years after the impact was not a matter of finding the right strategy. It was a matter of already having the right body and the right diet before the event occurred, which meant that nothing alive at the moment of impact had any ability to adapt in time. Evolutionary change operates across generations, across thousands of years at minimum. The impact winter compressed the selection event into a window far too short for adaptation to play any role. An animal either already fit the post-impact world or it did not, but the animals that happened to fit were not prepared for what they were surviving into. The small mammals in their burrows, the birds clinging to whatever seed stocks remained, the crocodilians sitting motionless in river mud, none of them had any mechanism to know that the world above them was not going to recover in weeks. They were not waiting. They were simply continuing to exist in the only way their biology allowed, in conditions that had become almost unrecognizable, with no food chains functioning above the level of decaying matter and dormant seeds. But the food that was available was not evenly distributed, and it was not going to last indefinitely. Dormant seeds in the soil represent a finite resource. Insects surviving on decaying organic matter depend on that organic matter remaining available. As the months of darkness extended into the second year, even the organisms that had survived the initial collapse were operating in conditions that were degrading further, and the ones that made it through were not necessarily the ones with the best strategy. They were the ones whose requirements happened to be small enough that the floor of what remained could still support them. The survivors were not the strongest or the largest. They were the ones whose way of living happened to match the only conditions that still existed. Small body size mattered because small animals need fewer calories. Dietary flexibility mattered because the animals that survived were the ones that could eat whatever was still available. Seeds, insects, decaying matter, rather than specializing in plants or large prey that had disappeared. The ability to shelter underground or underwater mattered because both environments buffered against temperature extremes and continued to offer some biological activity even when surface conditions had become lethal. Birds survived because the lineages that made it through were small, could eat seeds that remained dormant in the soil, and did not depend on the large forests that had been destroyed. Crocodilians survived because they were semi-aquatic, could go months without eating, and their metabolic demands were low enough that the depleted food chains of the early post-impact years could still support them. Mammals survived for the same suite of reasons: small, burrowing, omnivorous, metabolically flexible. The extinction followed a clear logic. The animals with the highest caloric needs and the narrowest diets died, and the ones with the lowest needs and the broadest diets lived. That logic would define not just who survived the impact, but who would come to dominate the planet in the millions of years that followed. The survivors were not lucky accidents. They were the product of exactly the traits that mattered in exactly those conditions. On land, the logic of survival came down to caloric need and dietary flexibility. But the oceans ran on different rules, and the impact hit the ocean's productive layer through a completely separate set of mechanisms. The same atmospheric disruption that collapsed land-based food chains reached the ocean surface within days. And what it did there dismantled a marine ecosystem that had been building for hundreds of millions of years, one level at a time, starting at the base. The oceans of the late Cretaceous bore almost no resemblance to the oceans today. The seas were warmer and shallower across their continental margins, and the surface waters teemed with organisms that had been building their populations since before the Jurassic. Ammonites, coiled mollusks with chambered shells, had been a constant presence in Earth's oceans for 400 million years, surviving every previous extinction event and diversifying each time into hundreds of new forms. Mosasaurs, some of them longer than a school bus, patrolled open water as apex predators. Plesiosaurs hunted fish and squid in the shallower coastal seas. Beneath all of them, microscopic phytoplankton converted sunlight into organic matter on a scale that supported every animal in the water above them. The surface of the ocean was where nearly all of this activity happened. Phytoplankton are photosynthetic. They need sunlight. Ammonites built their shells from calcium carbonate dissolved in seawater, which meant ocean chemistry had to stay within certain bounds for their shells to form correctly. Mosasaurs and plesiosaurs needed fish, and fish needed the smaller organisms that ultimately depended on phytoplankton. The entire productive layer of the ocean, the part where almost all marine life actually lived, was concentrated in the upper water column, the zone that received light and maintained a chemical balance that calcifying organisms required. That zone was also the part of the ocean most directly connected to the atmosphere above it. Whatever happened to atmospheric chemistry after the impact would not stay on land. It would reach the ocean surface within days, carried down by rain and gas exchange, and it would begin changing the water that hundreds of millions of years of marine evolution had been built around. But the ocean's response to the impact was not a single event. It was a sequence of overlapping disruptions arriving at different speeds, each one dismantling a different layer of the marine ecosystem before the previous disruption had finished. The tsunamis that devastated coastlines in the first hours rearranged shallow water sediments, burying reef structures and disrupting the seafloor communities that the productive nearshore zones depended on. That was the first wave of damage. The second arrived with the acid rain, which reached the ocean surface within days and began altering the pH of the water that calcifying organisms had spent 400 million years evolving within. But the collapse of phytoplankton was the one disruption that could not be compensated for. Every other marine organism at every trophic level ultimately depended on phytoplankton converting sunlight into organic carbon. Without that conversion, the entire cascade of energy that moved from microscopic algae to small zooplankton to fish to large marine reptiles had nothing entering it at the base. The ocean did not empty in a single moment. It emptied from the bottom up as each successive level of the food web lost the layer beneath it. But the timeline of marine recovery was even slower than the timeline of land recovery, because the altered surface water chemistry persisted as a barrier to calcifying organisms long after the darkness had lifted. The length of that persistence was what made this event different from earlier disruptions the oceans had absorbed. A barrier that lasts years is survivable. One that holds for thousands of years while populations shrink generation by generation with nowhere to recover to is not. The oceans absorbed the catastrophe differently from the land, but they did not escape it. The impact drove massive quantities of carbon dioxide and sulfur into the atmosphere, and both came back down into the oceans. Surface waters acidified rapidly. pH dropped enough to dissolve the calcium carbonate shells that most marine organisms depended on to survive. Ammonites, which had existed in the oceans for 400 million years and had survived every previous mass extinction event in Earth's history, could not survive this one. Their shells dissolved. The lineage ended completely. Mosasaurs and plesiosaurs, the large marine reptiles that had dominated open water for tens of millions of years, collapsed within years as the fish and squid populations they depended on fell apart beneath them. Phytoplankton, the base of almost every marine food chain, crashed as surface waters both acidified and lost sunlight during the impact winter. Without phytoplankton, the entire cascade of marine life above it had nothing to sustain it. But the deep ocean was different. Far from the surface disruption, in the cold and pressure of the abyssal zones, some ecosystems survived on the slow fall of organic material drifting down from above. Depth itself became a refuge, not because the deep ocean was unaffected, but because it was affected more slowly, and slowly was enough for some organisms to hold on. The pattern of survival in the ocean matched the pattern on land. The more isolated from the surface conditions of the catastrophe, the better the odds. 75% of marine species were gone. On land, the forests had burned, the plants had died, and the animals that required a functioning food web had followed them. What was left, across most of the planet's surface, was bare, acid-altered ground, with no large animals moving through it, and almost no plant life growing from it. The question was not whether life would return. It was what the very first steps of that return would look like, and where, exactly, they would begin. In the years immediately after the impact, the land surface of Earth was largely bare. The global wildfires had burned through vast areas of forest. The plants that had survived the fires had then died as photosynthesis became impossible under the aerosol-darkened sky. The soil, which, in a functioning ecosystem, is itself a complex biological community, held together by fungal networks and root systems, and billions of microbial organisms, had been exposed to acid rain that altered its chemistry and killed much of its biological content. What was left across most of the planet's land surface was a landscape of ash, dead material, and disrupted ground that bore almost no resemblance to the forests and grasslands that had covered it weeks before. Nothing large was moving through this landscape. The animals that had required a functioning food web to survive had already died or were dying. But something was still happening. not at the scale of animals or forests or any of the visible structures that the Cretaceous had built, but far below them. The recovery of the biosphere would begin with processes happening at the scale of millimeters, in the dark, in ground that had no plants growing in it and no large animals moving across it. And it would take far longer to produce anything visible than anything alive at the time could have waited for. But the question of how a biosphere recovers from near-total collapse is not straightforward, and the fossil record from the early post-impact years reveals something that complicates any simple narrative of return. The landscape that bacteria and fungi were beginning to process was not stable ground. The acid rain that had fallen for months had altered soil chemistry across vast areas. The temperature swings between the extended cold of the impact winter and the eventual warming as the aerosol layer cleared produced conditions that shifted faster than most organisms could track. Recovery did not mean returning to a starting point. It meant building on ground that had itself been transformed. But the ferns that appear in the fossil record immediately above the impact boundary were the fastest possible biological response to bare, disrupted ground. And the later stages of recovery that would eventually follow them were still entirely absent. A world covered in ferns had moved one step past total biological collapse. It had not moved further than that. The organisms that would come next were waiting on conditions that ferns alone could not yet provide. But the deeper problem was time. Each step in the recovery sequence required the previous step to be sufficiently established before it could proceed, and none of those steps moved quickly. Bacteria work at biological timescales, not geological ones, but the scale of the disruption they were processing, dead organic matter distributed across every continent, was vast enough that meaningful soil restoration took not years, but millennia. The mammals that would eventually diversify into the empty niches had to wait on a process that needed to rebuild every prerequisite from the ground up. And that process had nothing to do with the urgency of the niches that needed filling. Recovery did not begin with animals. It began with bacteria. Microbial life, which can survive conditions that kill every other living thing, was the first biological activity to reassert itself in the post-impact world. Fungi followed, breaking down the vast amounts of dead organic matter left behind. Then came the ferns. Fern spikes appear in the fossil record in rock layers directly above the impact boundary at sites across the world. Sudden, sharp explosions of fern pollen where almost nothing else existed. Ferns are opportunists. They grow fast, tolerate poor soil, and spread aggressively into open ground. In a world where every other plant had died and the soil had been disrupted by acid rain and temperature swings, ferns moved in first. They were not the end of recovery. They were the floor of it, the first layer of biological material that made it possible for anything else to grow. Recovery was not a single event or a steady progression. It was a sequence of dependencies, each step requiring the previous one to be in place before it could happen. Bacteria prepared the ground for ferns. Ferns stabilized enough soil and biological material for small flowering plants to follow. Those plants supported insects, and those insects supported the small mammals that were already waiting. Within 300,000 years of the impact, mammals had begun to diversify. The scaffolding was rebuilding from the bottom up, and it would keep rebuilding for millions of years before anything resembling the biological complexity the Cretaceous had maintained returned to the surface of the Earth. The recovery started in the ground, in soil that nothing visible was growing from, through processes that left no trace at the surface. Ferns followed. Then slowly, the small mammals that had survived began moving through a world that was just beginning to rebuild. But the emptied niches and the conditions needed to fill them were two different things. And the distance between those two realities would shape the entire trajectory of mammalian life for millions of years. For as long as dinosaurs had existed, mammals had existed alongside them. The earliest true mammals appear in the fossil record at roughly the same time as the earliest dinosaurs, around 225 million years ago, which means the two groups shared the planet for the entire duration of the Mesozoic era. That coexistence was not a partnership. It was a constraint. Dinosaurs occupied the large body-sized niches on land from very early in their history, and they held those niches without interruption for 150 million years. The competitive landscape the mammals inherited was fully occupied before they ever had the chance to move into it. What this produced was a mammal fauna that looked almost nothing like the mammals alive today. Mesozoic mammals were almost universally small. Most were the size of mice or shrews, and the largest known examples reached roughly the size of a badger. They were largely nocturnal, active during the hours when the largest dinosaurs were less mobile. Many were insectivorous or omnivorous, eating the foods that fell below the threshold of what large animals competed for. Some could glide. Some were semi-aquatic. What none of them were was large or active in the open during daylight, or occupying any niche that a dinosaur also wanted. That arrangement had held for longer than most people intuitively grasp, stable across a span of time that dwarfs the entire Cenozoic. And it held right up until a single event changed the conditions that had made it stable. But the mammals that survived the impact did not immediately expand. The world they emerged into was not a world of open opportunity. It was a world of collapsed food chains, bare soil, and an almost total absence of the plant communities that any larger animal would need to sustain itself. The ecological niches that the dinosaurs had vacated were not open in any useful sense. They were empty because the conditions that had filled them no longer existed. A niche for a large herbivore requires large amounts of vegetation. A niche for a large predator requires large herbivores. Neither of those conditions existed in the years immediately after the impact. But the mammals had no choice about when to begin. Reproduction does not pause for ecological recovery. The small survivors were breeding in a world that could barely support them, and many of the lineages that existed in the first years after the impact did not make it through the following millennia. The diversification of mammals into larger forms was not a rapid expansion into waiting opportunity. It was a slow process, dependent on the recovery of plant life, which was dependent on the recovery of soil, which was dependent on the recovery of microbial communities, a chain of prerequisites that stretched back to the very beginning of the post-impact biological sequence. But the specific direction that mammalian diversification took was not determined by the mammals themselves. It was determined by which niches recovered first, which plant communities established themselves earliest, and which geographic regions provided conditions suitable for larger animals before others did. The mammals that eventually became large herbivores were not responding to a plan. They were filling whatever space the recovering world made available, in whatever order that space became real. For 150 million years, mammals had been constrained, not by weakness, by competition. Dinosaurs had filled every large ecological niche on the planet, and the mammals that shared the Mesozoic world with them had adapted to the margins, small, nocturnal, operating in the spaces that dinosaurs did not occupy. That was not a failure. It was a survival strategy, that worked well enough to keep the mammal lineage alive across the entire reign of the dinosaurs. But when 75% of all species disappeared and the large ecological niches emptied, that constraint vanished. The mammals that survived the impact found themselves in a world that had been restructured around their existing capabilities. Small size, dietary flexibility, fast reproduction. Within the first few million years after the impact, mammals began moving into every available niche. Herbivores got larger, carnivores got larger. Specialized forms appeared where none had existed before. The asteroid did not just end one world, it created the conditions for an entirely different one. Every large mammal that has ever lived, from the first large Paleogene herbivores to the great whales, to every predator that has walked on four legs, to every primate that has ever climbed a tree, exists because of the space that opened in the aftermath of the Chicxulub impact. The extinction event was not only destruction, it was the specific mechanism by which the mammals that had operated in the shadow of the dinosaurs were given a world their competitors had vacated. The mammals diversified, slowly at first, then across every available niche as the recovering world made those niches real. Within 10 million years, the land supported large herbivores and large predators again, for the first time since the impact. But the world those animals were expanding into was not a reconstruction of the Cretaceous. The vegetation was different. The aerial dimension was being rebuilt from scratch by birds that had survived as small, generalized survivors at the margins of a world that no longer existed. What the Paleogene was assembling was something that had no prior template. By around 10 million years after the impact, the planet's land surface had changed in ways that went far beyond simply refilling the niches the dinosaurs had left empty. The vegetation was different. The Cretaceous had been dominated by conifers, ferns, and a spreading diversity of early flowering plants that had only recently begun to compete with the older plant lineages. The impact had cleared the field entirely, and the plants that moved fastest to recolonize bare ground were not the slow-growing conifers that had dominated the Mesozoic forests, but the flowering plants, whose seeds spread quickly, whose growth rates were faster, and whose relationships with animals had already begun forming before the impact erased everything. The Paleogene world that emerged was organized around those flowering plants in a way the Cretaceous world never had been. Forests grew back, but they were angiosperm forests, dense with fruit-bearing trees and shrubs that produced food in forms that mammals could exploit. The relationship between those plants and the animals expanding through them would become the defining biological dynamic of the Paleogene, shaping both lineages across millions of years in ways that are still visible in the ecosystems that exist today. Above the forest canopy, the aerial dimension of the Paleogene world was equally open. The birds that had survived the impact were beginning to move into it, and what that expansion produced over the following millions of years looked nothing like what had come before. But the Paleogene world that was assembling itself in the aftermath of the impact was not building toward anything predictable. The flowering plants that spread fastest into the cleared ground were not the ones that would eventually dominate every habitat. They were the opportunists, the fast-growing generalists, the plants that could establish on disturbed soil before competitors arrived, the stable, diverse angiosperm forests that would define the mature Paleogene took millions of years to develop, and, in the meantime, the mammals expanding through early post-impact landscapes were moving through environments that bore little resemblance to the complex ecosystems that would eventually replace them. But the birds filling the aerial dimension of the Paleogene were not simply occupying the same roles that pterosaurs had held. Pterosaurs had dominated the air for over 150 million years and had evolved into forms of extraordinary variety, some with wingspans approaching 10 meters. Others specialized for specific prey types in ways that had no bird equivalent. The birds that survived the impact were the smallest and most generalized members of a lineage that had existed during the dinosaur era. What they built in the Palagini was not a continuation of the Mesozoic aerial world. It was something assembled from scratch by animals whose prior experience had been limited to the margins of a world that no longer existed. But the Palagene's most significant biological feature was not what it produced in its first 10 million years. It was the relationship between plants and the animals moving through them, one that would compound in ways neither gave any early indication of, reshaping both lineages across the full length of the Cenozoic into forms that the early Paleogene world contained no evidence of predicting. The Paleogene world was not a restoration of the Cretaceous. It was something genuinely new. The forests that returned were dominated by flowering plants, angiosperms, which had been a growing presence in the late Cretaceous, but now, freed from the competition of the plant communities that had been destroyed, came to dominate land vegetation across the planet. These plants co-evolved with the animals recovering alongside them, producing fruits and seeds that fed the expanding mammal populations, which in turn spread the plants further. Bird lineages diversified explosively in the early Paleogene, filling the aerial niches that pterosaurs had vacated and the forest floor niches that small feathered dinosaurs had once occupied. The birds that survived the impact were the ancestors of nearly every bird alive today, and within a few million years, they had spread into forms as varied as large flightless ground hunters and tiny nectar-feeding specialists. The sky was not empty for long. What rebuilt was not a recovery toward what had existed before. It was an entirely new biological conjugation, built from the survivors of the old one, but organized around different plants, different animals, and different relationships between them. The world, 10 million years after the impact, looked almost nothing like the world 10 million years before it. The catastrophe had not paused Earth's biological history. It had redirected it entirely. The Palagene world that assembled itself over tens of millions of years, its forests, its mammals, its birds, left biological evidence in the fossil record that tells the story of recovery. But the impact itself left something different, a physical record embedded in the rock on every continent, at the same depth, deposited at the exact moment the Cretaceous ended. For most of the 20th century, no one knew what had put it there. When the answer was found, it changed not just the scientific understanding of the extinction, but the understanding of how quickly catastrophic biological transitions can happen. For most of the 19th century and much of the 20th, the disappearance of the dinosaurs was explained by processes that were gradual. Slow climate change, volcanic activity spread over millions of years, shifts in sea level that altered habitat. The fossil record showed clearly that dinosaurs had disappeared at a specific point in geological time, but the assumption was that the transition had been slow enough that no single cause needed to be invoked. Extinction events, in the prevailing view, were the product of accumulated pressures over long periods. That assumption held until 1980, when physicist Luis Alvarez and his geologist son Walter were examining rock samples from a geological formation in Gubbio, Italy. At a specific layer in the rock, the boundary between Cretaceous and Palagene sediments, they found concentrations of an element that had no business being there. present at levels orders of magnitude above anything in the rock above or below it. The layer they had found was not a local anomaly. When other research teams tested the same boundary at sites around the world, they found the same spike in Denmark, in New Zealand, in Spain, in ocean sediment cores pulled from the Pacific floor. A layer of material deposited at the exact moment in geological time when the dinosaurs disappeared, distributed across every continent at the same depth, everywhere. The question was what had put it there and what that meant for the speed and nature of the extinction that followed. But the iridium spike alone could not prove an asteroid impact. It could only prove that something had deposited anomalous material globally at a specific moment in geological time. The Alvarez team proposed the asteroid hypothesis in 1980, and the scientific community did not immediately accept it. The idea that a single extraterrestrial impact could cause a global mass extinction was not a hypothesis with obvious precedent, and the alternative explanations, prolonged volcanism in particular, remained credible to many researchers for years after the iridium layer was identified. But then, the crater was found. In the early 1990s, geophysical surveys of the Yucatan Peninsula and the Gulf of Mexico revealed a buried structure, a ring of cenotes on the surface. A gravity anomaly beneath it, a layer of shocked quartz and impact glass in the surrounding rock, consistent in every measurable way with an impactor of the scale the iridium spike had implied. The crater had not been visible because it was largely underwater and buried beneath material deposited long after the event. When the dates were confirmed, the structure matched the KPG boundary precisely. But what the crater and the boundary together confirmed was the sharpness of the line. That the biological transition recorded in the rock was not the product of gradual accumulated pressure over tens of thousands of years, but of a sequence of consequences that became irreversible far faster than the gradual extinction model had ever proposed, at a specific moment that could now be located, measured, and matched to a physical cause buried beneath the Gulf of Mexico. The evidence for the impact is not theoretical. It is physically present in rock layers around the world at the same geological depth on every continent. The KPG boundary, named for the Cretaceous and Paleogene periods it separates, is a thin layer of clay enriched with iridium, an element that is rare in Earth's crust but common in asteroids. When physicist Luis Alvarez and his team identified this layer in the 1980s and recognized its global distribution, it provided the first hard physical confirmation that an asteroid impact had occurred at exactly the time the dinosaurs disappeared. The boundary is extraordinarily precise. Below it, the fossil record contains dinosaurs, ammonites, mosasaurs, and the full fauna of the late Cretaceous. Above it, none of those animals appear. The transition does not happen over meters of rock. It happens within centimeters, representing a geological instant. In paleontological terms, the extinction was not gradual, it was sudden. The KPG boundary is not just a scientific curiosity. It is a readable record of the most consequential single event in the last 250 million years of life on Earth, traceable in road cuts, cliff faces, and canyon walls on every continent, that marks the exact moment the Mesozoic ended and the world that led to the present began. Everything before that line belonged to one history. Everything above it belongs to the history that produced the present. The KPG boundary is traceable in road cuts and canyon walls on every continent, a thin line that separates two entirely different biological histories. Below it, the Mesozoic; above it, the world that produced every large mammal that has ever lived. That world took 66 million years to arrive at its current configuration. Through multiple turnovers, through the rise and extinction of entire lineages, through a chain of contingent events that was set in motion in the minutes and hours of 66 million years ago. And understanding where that chain leads is what the final part of this story is about. The Cenozoic era, the 66 million years between the Chicxulub impact and the present, is the longest single era in Earth's history during which no non-avian dinosaur has walked the land. It is also the era in which every large land animal alive today evolved, diversified, and came to occupy the niches that the dinosaurs had held for the preceding 150 million years. That transition was not instantaneous. It played out across tens of millions of years, through climate shifts, through the opening and closing of land bridges between continents, through the rise and extinction of entire mammal lineages that no longer exist. The early Paleogene mammals that survived the impact were not the ancestors of any specific large animal alive today. They were the starting point of a diversification that would produce many lineages, most of which eventually went extinct before arriving at the fauna that exists now. Early horses were the size of dogs. Early whales still had legs. Early primates were small, tree-dwelling insectivores, living in the tropical forests that had re-established themselves across the equatorial belt within a few million years of the impact. None of these animals looked like what they would eventually become, and none of them were the inevitable outcome of the extinction event. They were possibilities that the extinction had opened, not destinations it had guaranteed. The impact had restructured the conditions under which land vertebrate life operated, and what that restructuring would eventually produce across 66 million years of mammalian diversification is a question the rest of the Cenozoic spends its entire length answering. But the Cenozoic was not a smooth progression from impact survivors to the fauna that exists today. The 66 million years between the Chicxulub impact and the present contain multiple extinctions of their own. The disappearance of entire mammal groups that had dominated their respective periods before being replaced by lineages that either outcompeted them or simply survived conditions they could not. The early large mammals of the Paleogene, the first animals to fill the niches the dinosaurs had vacated, were mostly gone by the Eocene. Their replacements were often gone by the Oligocene. The mammals alive today are not the descendants of the first animals to expand after the impact. They are the survivors of a 66 million year sequence of turnovers within the broader mammalian expansion the impact had initiated. But the primate lineage, which would eventually produce humans, had no indication of where it was heading during its early diversification. The first primates were small, tree-dwelling insectivores with no features that distinguished them as the ancestors of anything in particular. The path from those early primates to the lineages that eventually left the trees, developed bipedalism, and expanded across the planet was neither inevitable nor directed. It was the product of a series of environmental pressures, geographic separations, and competitive pressures that played out across tens of millions of years, most of which had nothing to do with any trait that would eventually matter for the development of complex cognition. But the question that the Chicxulub impact raises about contingency, about how different the present world would be if the asteroid had missed, is not one the fossil record can answer with certainty. What it can show is that the event established constraints on what was biologically possible on land, and that those constraints determined the range of what the Cenozoic was capable of producing, including everything it eventually did. The Chicxulub impact is not a story that ended 66 million years ago. Every mammal alive today, every dog, every whale, every bat, every primate descends from the animals that survived that event. The primate lineage, the one that would eventually produce humans, began diversifying within 10 million years of the impact. Without the extinction of the large dinosaurs, that diversification would not have happened. The ecological space would not have been available. The mammals that eventually produced the primate line would have remained small, nocturnal, and limited to the margins as they had been for the previous 150 million years. The asteroid did not cause human evolution, but it removed the one condition that had prevented it: the dominance of dinosaurs over every large ecological niche on the planet. What followed the impact was a 66 million year sequence of mammalian diversification that eventually, through a long and contingent chain of events, produced the species that is now able to look back at the impact and understand what it was. The aftermath of the Chicxulub impact is not ancient history. It is the direct cause of the biological world that exists today. The reason mammals dominate the land, the reason the oceans are filled with whales rather than mosasaurs, and the reason the Cenozoic unfolded into the most mammal-dominated era Earth has ever seen. The asteroid ended one world completely. The world it left behind became the one that exists today. If this is the kind of thing you want more of, deep dives into the events that shaped the planet, told slowly enough to actually stay with, subscribing keeps these coming.